In this video, we're going to talk about Gauss's law, specifically the fundamentals. In the next video, we will apply Gauss's law. To begin, remember that an electric field is a vector field. So, consider our electric field E going through some area A. Well, then the flux is the amount of that vector field that goes through a certain area. Now in this case, let's say that E is parallel to the normal vector. That means E is perpendicular to the area. Well, then the flux is just really the magnitude of E times the area. Now consider E going through our area at an angle theta. We want to know the amount of E going through A. So that would be the perpendicular part of E that's perpendicular to A. So then our flux is the magnitude of E times cosine of the angle times the area. And if you notice, since E is a vector, we can write A as a vector using the normal vector. We can write the flux is E dot A, where A is our magnitude, our area, times the normal vector. So then we can generalize the flux, considering a small piece of area on a surface. The flux of that small piece was labeled N is E dot the normal vector times that small area dA. So for the entire surface, we're just going to add up all the infinitesimally small dAs, and we get that flux is the integral over the entire surface of E dot N dA. Or the flux is the integral of E dot dA vector. Next, let's look at how Gauss's law comes about. If the flux is how much of the electric field goes through the surface, let's consider two situations. One, consider a charge Q inside a box. From that charge Q, the electric field is going to radiate outward along the radius vector. So we have a flux going through each side of the cube, going out. Now consider a charge Q outside of the box. The charge Q will radiate a field outward through each side of the cube and out. So there is no flux. Therefore, the flux is proportional to the charge enclosed. And from experimentation, we get Gauss's law, or the integral of E dot dA is equal to Q enclosed over epsilon sub 0.